Module 12E of Physical Science. This is our last video in the module. We'll be talking about magnetism. The vocabulary for Module 12E: North pole of a magnet, south pole of a magnet, dipoles, monopole, and magnetic field lines. So let's talk about magnetism. In a previous module, we had actually done an experiment that involved wrapping some wire around a nail, and we created our own magnet by attaching a battery to it. And a lot of what we're talking about here has to do with that experiment. The force that's involved in electricity is the same force that is involved in magnetism. We have studied 4 physical forces, and many scientists consider electrical force and magnetic force to be the same, so they consider there to be only 3 physical forces, the third force being electromagnetic force. It's important to study magnets and magnetic force to further understanding of the electromagnetic force. In Module 6, we learned that the movement of charged particles, or electrons, create a magnetic force, and all magnetic force results from the movement of charged particles. So magnetic force can be generated by the movement of charged particles, even though some magnets are permanent and do not have electricity hooked up to them. So just as a review, all matter is composed of charged particles. And this is why, even if a magnet is not hooked up to electricity, it can still carry a magnetic charge. All atoms contain positively and negatively charged electrons, and those electrons in atoms are in constant motion. For a material to be magnetic, its atoms have to line up in a certain way so that the electrons all have the same general motion. So they'll all be traveling along its same path. Most materials don't have atoms that align all in the same direction. So most materials are not magnetic. The electrons in most atoms have random motion. And the result of random motion is that the individual magnetic fields generated by all of the atoms' motions cancel each other out. So you have positive and negative canceling each other. There are materials, though, that under certain conditions can have their atoms arranged to have the electrons in the same general motion. And once again, if those atoms are arranged in the same general motion, the result will be a magnet. One of the materials that can become a magnet is iron. If iron is exposed to electricity, it will carry a magnetic charge for a short time. If exposed to electricity for a long time, iron can permanently become a magnet. And here's an example of the flow chart of the experiment that we did. We had a battery, and there was a wire coming out of the positive side and the negative side of the battery. And the wire was wrapped around a nail, and whenever we attached the wire to both poles, the nail became magnetic. There's an actual flow of electrons in the nail that would speed up when the electricity was attached to it. And the more coils that we have on that nail, the stronger the magnetic force will be. So let's use this picture as the idea of a magnet. Magnets have a north and south pole, like this bar magnet in the picture above. Because magnets come in pairs, they're called dipoles. di meaning two. There are some scientists who believe that there might be a magnetic pole that is by itself. So they're looking all over the world for some kind of material or some kind of situation where you would just have a North Pole or just a South Pole on a material. And if they ever find it, or if this would be possible, it would be called a monopole. If you were to split a bar magnet in half, it's intuitive to think that you would have a magnet's North Pole on one side and its South Pole on the other. In other words, that you would have two magnets. One would be north and the other one would be south. But in reality, what you would have would be two magnets that would have both north and south poles. This is because the magnet's alignment of atoms would alter once split to create north and south poles. So in reality, you really can't split a magnet into two separate poles. If only a fraction of the atoms in the material align in the same direction, you'll have a magnet. But the more atoms that line up, the stronger the magnet. So, as the example with the nail, when we applied electricity, we created a magnetic force. But the more coils that we wrapped around the nail, the stronger that force became. That's because it actually caused more motion in the atoms. And as those atoms lined up, the stronger the magnet became. So the strength of the magnet depends on what percentage of the atoms in the material are aligned. The magnetic force is directly proportional to the strength of each pole involved. And the strength of magnetic force is also inversely proportional to the square of the distance between the poles. Does this sound familiar? Well, this similarity to the properties of electricity is explained by the fact that electricity and magnetism are just different aspects of the same force. So the reason they lump them into one force is because their atoms actually work quite similarly. Consequently, the force between the poles of a magnet behaves the same as the force between charges. The force between the poles of a magnet can be illustrated with magnetic field lines similar to the illustration above. You may have done an experiment in the past where you had iron shavings on a piece of paper and you placed a magnet underneath them and saw these actual field lines lined up like this on the paper. This is one of the ways that we can actually see the field lines. Another picture that we've seen where it showed something similar was a picture of the magnetic fields around the Earth. So this is it for Module 12, and if you have any questions, be sure to contact me.